Welcome to ETHDam, to ETHDam, to ETHDam, to ETHDam, to ETHDam.
So today we will talk about FHE a little bit and ZK and how they play together. So I'm Lauri. I'm a freelancer doing ZK EVM development. Been doing it for some 7 years now, and maybe like 2 years ago I focused more on the ZK side. So what will we actually talk about? So there's these two difficult concepts that I actually mentioned. There's the zero knowledge called ZK, and the second one is FHE, which is fully homomorphic encryption. It's a mouthful, but hopefully we will understand a little bit how it works and what it enables. So we will quickly go through what these two are, what kind of use cases they enable, how they work a little bit. Then there are some challenges because they are rather complicated topics, so there are some challenges in how to use them, how to learn how they work and how they can be utilized, and some comparisons. So, well, let's start from the ZK part, and let's actually start what does it mean to be zero knowledge. So the actual term is used quite in different contexts, and it means a bit different things, which causes some confusion. But in a strict sense, it means that we have some privacy. So we have some data, and if we transmit it, the receiving party gets zero knowledge of the original data. So there's zero data is revealed of just some properties that we want to reveal, but not the actual data. So in ZK, there's these two entities, prover and a verifier. So we have a prover, and they want to prove, they have some claim. For example, I have a number, or I have some certain algorithm that I want to prove that I have these things. And then there's the other party, the verifier. Okay, I have a claim, I prove it, and then someone wants to verify my claim. Or is your proof valid? Do you actually have what you claim you have? And then these two interact in certain patterns. So there's two ways they can interact. They can either do it interactively, so they kind of talk with each other, and the verifier asks like more details or more challenges. Or then there's just like non-interactive. So the prover kind of publishes the proof somewhere, and whoever wants, they can verify it. So the flow starts with claim. Like you have your claim. Maybe I have a secret number I don't want to reveal for some reason. And you input this into a special prover program. You can write this yourself, or maybe someone else has written it for you. And this outputs a proof. So this proof is just kind of like a random string, which you can then input into a verifier program. So once you have this proof, you can verify with this special verifier program whether the proof is valid or not. And the verifier and the prover, they are tied to each other quite tightly usually. So they have the context, like the verifier knows what I'm verifying. So you cannot verify other proofs usually. It depends a little bit also. So this enables two main use cases. Verifiable computation. So it means you have this goes back to the algorithm, that you have some claim about algorithm, or you have some computation that you want to prove that you did it correctly. For example, you can ask your cloud provider to do some computation for you, and then they can prove that they did what you asked them to do. But this can also be used for scaling. So if you have some computation, well, blockchains are about computation. So you can scale your blockchain, especially like L2 rollups, by using ZK, just to prove that you have done the block production and all these rules. But the second use case is the privacy. So you have some data that fits some criteria, and you define what are the criteria, but you don't want to reveal the data for whatever reason. So these for like whatever financial transactions you have, maybe like just blockchain transactions, or just any stuff you do online in the internet. So the bigger picture is that you have these two entities, like the prover and verifier, and they are somehow connected. Maybe they talk to each other, or they are just like non-interactive, but still you have this. And then you have someone who wants to who has a claim and they want to use a prover, okay? Now I have a claim, I will go and use this prover, and out comes a proof, okay? And someone wants to verify this proof. Otherwise, like, you generate a proof, but nobody cares about it, so what's the point? So there has to be someone who cares about this proof, so they get the proof in some way from some online database or whatever. So they get this proof, but what do they actually do with it? Well, they ask the verifier program, like, okay, now I give you the proof. Is the proof valid or not? And this is kind of like a bit complicated already. But then there's all sort of like nuances on top of it, like some technological stuff like trusted setups and like different trust assumptions. For example, like you have this verifier, but how can you trust what it does? So you get this program from somewhere, but how do you know it verifies what you think it verifies? So this leads to like underneath there's all sort of different mathematics. Like we're not gonna go here, but all sort of different weird shit. So it's super complicated, and just don't go there. Like smarter people do that part, luckily, and we don't have to touch that. So the typical learning path is like, first you try to understand this. What does the term mean, and what is zero knowledge? And then you're like, okay, well now I maybe understand something. What are the use cases for it? Where can it be used? So was it like privacy, or was it something else? And or like how do they discuss? Well, like did they talk each other with each other or not? Like you're starting to get a bit confused. Like how does the system actually work? And can I trust the verifier? How can we establish this kind of trust connection? And then at some point you just say, screw that shit. Like this is getting too complicated, and it's difficult to architect this kind of system also. Like is it worth it? So let's take a few steps back. Let's imagine this like awesome service. A service that doubles any number you send it. So we send number 4, it gives us 8. Awesome. We have a great service. But then the next question is, can we add some privacy into this kind of service? Yes and no. We can encrypt our value. So we encrypt number 4 and send it to this awesome service. And what do we get back? Well, we don't get anything back. Like the service cannot do anything with the data because it's encrypted. We have full privacy, but we get nothing back. So it's totally useless. And this is something that FHE will fix, and where it actually shines very well. It's the same system. We encrypt number 4. We send it to this service that supports FHE, and they send encrypted 8 back. And the service itself, they had no idea what they doubled something, but they have no idea what they doubled. So the only one who knows the number 4 and number 8 is the original user who encrypted it. So this is the beauty of FHE. And if you kind of compare like these schemes and designs, how they work, it's a bit obvious like which one is easier to understand and to architect. So for FHE, the learning path is a bit different, I would say. Point 1, you have some data, you encrypt it, and other people can compute based on the data. And that's about it. There's nothing else basically you have to learn about it. So they both offer privacy, but how ZK does it is just totally different way. They do it like there's the prover and verifier interaction, and it's a lot more complicated. And with FHE, it kind of just works. And of course, like it's not a silver bullet. It has its own issues. There's a lot more processing, and there's lots more research needed for FHE. But in theory, it works a lot easier. So ZK works, and it has been established, and a lot of projects use it. It's great, fine, but it's complicated to get into use. So FHE somewhat works, but it's a lot more easier to understand and to explain and to take into use. So if FHE can get their research done and they can get their shit together at some beautiful day, then it will probably eat many of the use cases, especially the privacy use cases that ZK provides today. So illustrated conclusion, we will just eat all the ZK privacy some beautiful day. Let's see. yeah, that's my slides. Thanks.
Thank you. I love the advice of getting your shit together, so I really like that. And we've got time for a few questions. Perfect, over here. Cool.
What tools are there out there right now that people can use to implement this on-chain or off?
You mean FHE? Yeah, that's there's not too much on-chain stuff. Zama is doing some, and then there are a few other projects. But I think those are, in theory, they work, but I think the computational effort is way too much still. So you cannot, in real life, you cannot use it yet.
Cool. Do we have any more questions? Yes? No? Cool. If you think of any questions later on in the day, Lauri will be walking around. So thank you so much.
Thanks.